Welcome to sorting and searching. Sorting arranges data in order, and that order is what makes searching fast. This chapter builds 5 sorts: insertion, selection, merge, quicksort, and heap sort, and each one trades simplicity against speed and stability. It also covers binary search, which is very fast but only works once the data is sorted. Let's start with why sorting and searching matter so much. The speed of every search you do later depends on getting the data in order first. Let's look at the goals for this chapter. By the end, you will be able to do 4 things. First, you can trace one pass of each sort. That means insertion sort, selection sort, merge sort, quicksort, and heap sort. Second, you can tell a stable sort from an unstable one. A stable sort keeps 2 equal items in their original order, and an unstable sort may swap them. Third, you can count comparisons and swaps. That is how you see why already sorted input helps some sorts and hurts others. Fourth, you can connect sorting to search speed. A sorted array lets you use binary search, which costs big O of log n instead of big O of n. One idea runs through the whole chapter. Every sort trades 4 things: comparisons, moves, memory, and stability. Once you understand those 4, you can pick the right sort instead of memorizing 5 separate algorithms. 2 everyday habits already show the 2 ideas in this chapter. You have probably done both of them without knowing their names. Think about sorting a hand of playing cards. You pick up cards one at a time and slide each one into its place. The cards already in your hand stay sorted the whole time. That is exactly insertion sort. Now think about finding a name in a sorted phone book. You never scan from front to back. You flip to the middle first, and if you land too early, you flip right, and if too late, you flip left. That is exactly binary search, and it only works because the book is already sorted. Back in Chapter 2, binary search found any value in a sorted array in about log base 2 of n probes. That is roughly 20 probes across 1,000,000 elements, but it has one strict requirement. Binary search only works on sorted data. If the data is not sorted, that speed is gone. On unsorted data, the best you can do is a linear scan. You check every element one by one, and that costs big O of n. So to get big O of log in search, something must sort the array first. The obvious way to sort is to compare pairs of elements and swap the ones that are out of order. So the chapter starts from one fact: binary search is useless until the data is sorted. The real question then becomes, how expensive is sorting? The obvious sorts, like bubble sort and selection sort, compare almost every element against every other element. For n elements, that is about n squared comparisons. Let's see what n squared really costs. With 100 elements, n squared is 10,000 comparisons. That feels instant. With 10,000 elements, it jumps to 100 million comparisons. Now you feel a pause. With 1,000,000 elements, it is about 1,000,000,000,000 comparisons. That takes minutes to hours. And 1,000,000 items is not large. It is a phone's contact list or a mid-sized database table. Comparing every pair is still 1,000,000,000,000 comparisons, and the progress bar would crawl. Here is what those numbers mean. Big O of n squared, double the input and you quadruple the work. At 1,000,000 elements, it has already stopped being usable, not slow, unusable. There has to be a better way, and there is, which is what the rest of this chapter is about. Merge sort and quicksort never compare every pair. They split the problem in half again and again, so the cost is n log n, not n squared. Let's compare the same sizes. With 100 elements, n log n is about 700 comparisons instead of 10,000. With 10,000 elements, it is about 130,000 comparisons instead of 100 million. With 1 million elements, it is about 20 million comparisons instead of a trillion. Same million elements, 20 million comparisons instead of a trillion. That is a 50,000 times cut done before you even notice. Put a number on the gap. At a million elements, big O of n squared against big O of n log n is the difference between hours and an instant. That gap is why merge sort and quicksort exist, and it is why the rest of this chapter matters. Divide and conquer wins at scale, but just saying use quicksort is not the full answer. So why do we need more than one sorting algorithm? A tiny or nearly sorted list favors a simple, adaptive sort. Adaptive means it runs faster when the input is already close to sorted. A huge list favors a sort with a guarantee big O of n log n, and sometimes you pay for that guarantee with extra memory. And quicksort itself can collapse back to big O of n squared on the wrong input. So different sorts win on different inputs. Just sort is not one single decision. This chapter is a comparison, not a list. Every algorithm is judged on the same 4 axes, so by the end you can defend a choice, not just name one.